So what stuff could we add to this periodic table to help us?
This staircase.
Okay. We've got that staircase, which I think is here. Is that exactly it? Okay. There's our staircase. What else could we add?
The border between hydrogen, helium, and the rest.
Okay. That's a good point. I forgot about that one. So that we don't confuse, which will be important when we get into chapter 5 and a little bit of 4, on recognizing that hydrogen and helium are kind of lifted off, and so we don't overplace them as, or for sure, we don't overplace hydrogens as metals, that it is a non-metal. Okay.
Yeah, because the one that was in the book actually had hydrogen sitting in the center, like not even attached to the table.
Yeah, I've seen that one too, actually, where they take hydrogen. Helium usually stays above neon, but they'll sometimes float hydrogen and sometimes helium out in the middle. But that tends to be a little bit more rare. I did kind of make a statement on what else we could identify on this.
Mark our liquids.
Okay, we could mark our liquids. So mercury
And boron.
and
bromine.
boron,
Bromine.
not boron, but bromine. So this is where we have to be careful with the letters and those symbols. So those are the blue ones on the wall. Okay? The periodic table that I would recommend you study with and practice with would be the second page of the practice exam. Okay? Because that's the periodic table you're going to have on the exam. You'll have the ones on the wall, but that could be harder to interpret because they're further away. If you do the one from the practice exam, that's a little bit more comforting, or not say comforting, but more used to it. And I believe the way I've got that marked is like a circle in the upper right-hand corner of those two. All right? So we've now identified our circle as a gas. Sorry. So I start giving away more stuff. Is it a liquid? What else could we identify?
Our gases.
Our gases, which on our periodic table up here are all in red: nitrogen, oxygen,
The entire column.
and then that one. I almost always forget this last column, which would be ideal if we talked about it today, but we'll see. Okay. The periodic table, or how I've got that done on your exam, is I believe an X in the upper left-hand corner.
Yeah.
Okay. Why am I using X's and circles as opposed to color coding? Color coding's expensive. It's kind of silly, but that's what it is. Okay? So the X's would be our gases. Unmarked or black would be our solids. So that's extra information we've got on there. So cool. What else could we pull?
You could do like the groups and periods.
We haven't addressed groups and periods yet. That would be something that would be relevant. Let's try and keep our focus first on what we talked about on Tuesday.
Identify the metalloids.
We could identify the metalloids. As we talked about on Tuesday, metalloids become a little bit trickier to detail out because it's not exactly on the staircase. Okay. Some of the elements touching the staircase aren't metalloids. Some of them are. So that exact differentiation can be a little bit more challenging. What I would argue you should remember. Were you about to suggest this?
No.
You're going to do something else? Okay, we'll come back to that. To the left of that staircase, we have metals. And then to the right, we have nonmetals. Okay? So this is relatively simple information to be encoded, and you might just internalize it and not worry about writing it down. That's up to you. Okay? What were you going to suggest?
I was going to say with the metalloids if they were in the staircase, but she said.
Yeah, so she addressed the metalloids. I personally have a hard time memorizing which ones specifically. So if you want to do that, that's fine.
Are you going
But-
to ask us?
If I personally have a hard time with it, what do you think is going to happen when it comes to an exam
You're
question?
going to be mean and you're going to put it.
Okay, more than likely I wouldn't ask that question. Okay. if there's cases where I personally have a problem with something, I will be explicit and be like, I'm going to ask this because this is something that you should know, even though I don't. Okay? That's rare. Very, very rare. Okay? So cool. We've got some information coded on our periodic table. We can now start to pull that out. You guys have been working on memorizing your elements?
In Spanish, I got.
Like right to the list.
Oh, that's cool. Okay, Spanish isn't necessarily a bad thing for getting them nailed down. I will say it becomes trickier on a test because on a test you have multiple choice where they're not written in Spanish. So you'll get some overlaps because English is not in that foreign from Spanish in a lot of the roots. So you'll probably be okay, but be aware you should probably review some of those. Okay? Everybody else has been working on them? Yeah? Symbol for nitrogen? Not Ni? What is it? Nitrogen, N-I-T. Why is it not Ni? Because nickel is Ni. Okay? So we have to be very careful with some of these. There's a lot of overlap. Those ones where you're like, oh, I would get nickel and nitrogen confused. Guess what shows up on a test question? Nickel and nitrogen. Okay? So be aware of that when you go through and look at these, is look for those things where you're like, those are easy to confuse. If they're easy to confuse, they are very common test questions.
Now, in the reading that they were talking about, they start off with the first letter and then go to the first, second or third letter. Was that just because of the order that they were discovered in, or?
Some of that is that, yes. So if you look early on, a lot of them are just first letters.
Right.
Okay, but helium is the second one, and that's 2 letters. Order of discovery, helium was discovered very, very, very late. Hydrogen had been discovered first. That's why we go He. Lithium, Li. That's still 2 letters. That's the third element. The order in which it was discovered. The order, so you could look at this and go based off of order of discovery and say, oh, boron, carbon, nitrogen, oxygen, fluorine were probably all discovered before lithium, beryllium, sodium, magnesium, and all those, right? So it's a neat observation, but you're not responsible for those discovery dates, so I wouldn't stress on that. Okay?
Yeah, I was just wondering if that's why it ended up that way.
So that contributes to some of it, yes. Okay? Because if I asked you to come up with an abbreviation, you're going to come up with the shortest abbreviation possible. That's why we went to 1 letter. And we go, oh crap, I can't go to just 1 letter, I have to go to 2. Okay? Tungsten. Symbol for tungsten. Why is it a W?
Yeah, a different name before.
Because of its Latin.
From of the origin language. Who discovered it? Where did they discover it? They got to decide what the name was. Where is tungsten typically found? In the mineral wolframite, which begins with the W. Okay? So and I think that mineral name is so called either after the location or the discoverer. I don't remember which one. Okay? So some of these make a lot of sense, some of them don't. Okay? Greg kind of geeks out on a lot of the origins of these because there's different explanations for why those symbols were chosen. Okay? So, with that, we're going to move into chapter 4. We get a little bit of what I called a history lesson. And I had a student say that they hated history and it was awful. And so I was like, oh, great, that's exactly what I'm about to teach you today. And he said that this wasn't exactly a history lesson. I still think it's a history lesson. So there's lots of kind of facts that flow through this. You're not responsible for each and every individual fact. Okay, what you're responsible for is some key ideas. So we'll talk about it, and then I'll say what I would expect you to have memorized, at least in a few of those cases. Okay, so you get a better context of it. So, starting off, Dalton's atomic theory, early 1800. I don't care that you remember early 1800. Okay? What I do care is that you've got Dalton's atomic theory and tied to these 5 pieces. Why is the early 1800 there?
That sounds crazy.
Give you kind of a timeline, a context behind these discoveries. Okay? So that when we go through and look at them, we could be like, oh, that's an awful stupid idea. Why is it an awful stupid idea? It's early 1800. We hadn't discovered a whole lot of stuff. Okay? So it's trying to show that building process. Okay? Before we actually go through the theories, the other image that's shown on here, I just need to delete the sun thing because I think that's stupid now. Okay? What are we looking at in these pictures? Okay? It's close. It's not in a periodic table. This section is a periodic table.
Compounds.
Okay?
And then the bottom one is supposed to be the most common compounds that he
The
found?
bottom ones are the compounds. So we talked about the difference between elements and compounds, okay, or atoms and compounds. We've got the elements up top, and then we're combining those elements in different ratios to get the different compounds. Okay? If you go through and look at that notation, what do you think? Is that a good notation or a bad notation? Bad. Why is that a bad notation?
I don't know which one is which.
Which one is which? Okay? So you're saying you don't understand those symbols because those are silly symbols. Okay? But if I said the silly symbol of a straight line and 2 curvy bits, you're like, oh, that's okay? How is that any different than a dot with a circle around it? Okay? It's just a familiarity with it. We haven't had that familiarity with those shapes. We're more familiar with the shapes of the alphabet that we're used to working with. Okay? But it's ultimately the same process. Okay? Eventually, what we'll discover is that the variability that we can get with a circle and a dot and being able to easily distinguish them up to 118 becomes difficult, and we need a different system. Okay? We can't use just single letters, because single letters get us
26, right?
26. Different alphabet.
Yeah.
Not 118. So we have to use combinations thereof. Okay? And that's why we're getting that variability. Why did Dalton only have that many elements?
So discovered.
That was all they had discovered at that point. Okay? There's a lot more compounds than that, but those were the ones that he had data on that he could say these are the combinations thereof. Kind of make sense? Okay. So, his theories. Number 1, an element is composed, for a moment I thought it said of fairies, of tiny, indivisible, indestructible particles called atoms. Okay? Before this, we didn't actually define the smallest piece. So Dalton actually went through and said, know what? Everything has the smallest piece. We can divide and divide and divide until eventually we're done. There's nothing smaller. And that, I'm going to call an atom. That atom can now go out and do other things. Okay? What things could it do? Okay, well, before we get into that, we first address what an atom is. Okay? Not only is it this tiny piece, okay, but each atom is the same as every other type of atom. So if I have a carbon atom that I pull out of carbon dioxide, okay, a gas, and a carbon atom that I pull out of wood, those are the same atom. Okay? I can't tell the difference from where they came from. All I've got is that it's a carbon atom. Okay? What I can do with that atom, though, is I can combine it with other elements to form compounds. Okay, so those compounds are going to have different properties. That's why when we pull carbon from CO2, CO2 has a different property than wood. Okay, because the compounds being generated are different. Okay. Atoms of different elements combine to form compounds. I literally just said that. It helps if I focus where I'm reading. 4, compounds contain atoms in small whole number ratios. Okay, my argument is that 4 is really a natural conclusion of what? Of 1. Okay, if I can't break apart the atom, I can't have different variables. Okay, they can only be single values, okay, or whole values. I can have a whole bunch of one type of atom, but I can't have fractional values. Okay, 5, atoms combine in more than one ratio to form different compounds. Okay. So it's not just that I combine two atoms and now I have a compound and all of my compounds are a composition of two atoms. I could take a whole bunch of different atoms and put them together. Right? So the fun joke for 5 is, of course, going into a bar. Right? I have no idea what you're talking about. Two guys walk into a bar. The first one says, I'll have a glass of H2O. The second one says, I'll have a glass of H2O2. Second one dies.
Oh, yeah.
H2O2 is hydrogen peroxide versus H2O being water. Okay? So by changing the combination, we can get drastically different compounds. Okay? Was Dalton right? Wait, is that joke sinking in now?
No, it's just that, yeah.
Okay.
It took me a while.
That's
I
fine.
got it the scientific way, not the dumb way.
Yeah. Yeah, if Greg's here, Greg's usually responds and says, they both live because the bartender understands contextual clues to understand that 2 did not mean TWO, it meant TOO. Way to break the joke. Okay. So those are our rules. Do any of those rules stand out based off of your readings as being wrong? The first one. Do we have particles smaller than atoms?
Yes.
Yeah. Namely, protons,
Electrons.
neutrons, electrons. Okay? Anything else?
The second one,
Okay, the second one, what's wrong with the second one?
they don't have the same properties.
What do you mean?
Well,
Isotopes.
they're not, there's gases, solids, and,
So gases, solids, and liquids are an amalgamation of those different atoms. Rule 2 is just saying I have one atom and one atom. If I only have one atom, I can't define that as solid, liquid, or gas. I'd have to see its context with a whole bunch of other atoms. So solid, liquid, gas isn't a bad idea, but that's not going to allow me to differentiate or invalidate 2. Okay? What were you going to suggest?
Isotopes.
Isotopes. What are isotopes?
They have, they're the same element, they have different, molecular mass.
Okay? The same this different atoms of the same element can have different masses, which sounds really kind of bizarre until you understand subatomic particles, which is why Dalton didn't theorize that process, or why he came in and said they were all the same. Because when we look at an individual atom, it looks to be the same based off of initial observations. Okay? We would have to really refine our equipment to be able to prove 2 wrong. Okay? That proof for ultimately both 1 and 2 failing, okay, comes out with Thomson. Okay, late 1800s. We're talking 1890s, I think. So roughly 100 years later, Thomson comes out and he discovers the existence of an electron and thereby also postulates the existence of a proton. Okay? In his discovery, he notes that an electron has a negative charge and a proton has a positive charge. These are relative charges. So what he's able to say is that relatively there's this particle that has some negative characteristic. There also has to be a particle that has some positive characteristic, okay, to counteract that. Why? What if there wasn't a positive particle walking around?
How would you know that the other one was negative then?
Interesting idea.
Scientists,
Yeah, I could accept that. Okay, that works. How would you know one was negative if there wasn't a counterbalancing argument? One of the options that you can come up with is magnets. Magnets don't strictly have a positive and negative, but they do have a polarity to it, and that's ultimately how we discovered that we're getting a charged particle. Right? And we'll look at that discovery in a second. What else? One I like to use at least.
Maybe there would be no attraction between atoms.
Okay, so that could change the attraction between atoms. Okay, if electrons could just exist and float around, what happens when you walk around? You're going to encounter an electron, right? Where are electrons?
in the atom.
In atoms. And in this room, where could you point to a big source of electrons? Sort of in the lights. It's what powers the lights. You mean the electrical outlets. Right? You ever stuck a fork in an electrical outlet? Some people said yes. Wow. Dang, you had an interesting childhood. Okay, don't do that. Okay, you should be told not to do that. Okay, why not? You get shocked. What's coming out of the electrical outlet? The Wrong. It's electrons that are coming out of it. If electrons were just existing around, what happens is you walk. You would get shocked. There's an opposing particle to neutralize that charge so that we don't feel that shock. Right? So we've got electrons and protons. We have not defined the exact value of that charge, and ultimately the exact value does not matter. We just need to know that whatever the value is for a proton is the same for an electron, but opposite. Electrons being negative, protons being positive. The numerical value we tend to associate with them is 1, but it is kind of arbitrary, as we'll see here in a second. First, Ali, and then we'll go over.
So I have like a weird question. In one of my other chemistry classes in high school, my buddies stuck like a pencil in the electrical outlet and then he got shocked too. But the pencil doesn't have any like metal like properties to it, so why would it?
Are there materials that conduct that aren't metals?
Yes.
Yes. The pencil lead will conduct electricity.
But it was like bare, like it was like more wood than actual lead. So
It-
was it like that very minimal lead?
It's probably that little bit of lead. Okay? Electricity can jump. Electrons do some bizarre stuff. Okay? For instance, you've seen lightning, right? What is lightning? Electrons. What's the metal coming from the cloud to the ground, allowing the electrons to move through the sky? Is that a metal? Where's the metal rod in the sky coming down to the ground so the electrons can jump?
Would it be like,
Okay? It builds up enough of a charge that it can bridge that gap, and it will jump across ions through the sky. Okay, so there are other materials that will allow for the passage of electricity. Those materials need very particular conditions and better alignments than, say, a metal. A metal will do it naturally on its own.
Okay, so I don't know if this goes with this part, but if you have a +8 on protons, isn't it a noble gas or something like that? No.
We'll get there, not yet.
But it's somewhere there.
You have parts that are right and parts that are wrong.
Okay.
So we'll get there to address that. Okay. The thing that I think is fun here is a little bit on the history is what does this hinge on? What did this discovery wait for? Why did Dalton not have this theory further on?
technology?
What was the technology? What was the technology advance?
Electron microscopes?
Nope, not electron microscopes. Not light bulbs. They were studying electricity, that's true, okay, but that doesn't allow us to understand that electricity was electrons. A vacuum. Not necessarily the vacuum cleaner, but a vacuum. A vacuum was the initial technology that was then adapted to become a vacuum cleaner. Okay? Why do I need a vacuum? Right, well, we know electricity moves through metals. Right? What if I have a container that has nothing in it? What should the electricity do?
Nothing.
I don't know, right? How could it possibly move through there? Right? Because I know electricity has to move through a metal. I can see it move through sky in particular cases, but how do I replicate that in a container? So what they did is took tubes with a bunch of electricity on either end to try and see what would happen. Right? And ultimately, they don't see much. Okay? Nothing really happens. Right? And that's because when that charge is generated, it impacts atoms. Those atoms kill the charge right away. Right? What happens if you take that same tube and you remove all the atoms?
Then you'll get electricity out of it.
Now we would say, well, nothing should pass through. Right? And what instead happens is we see a bizarre glow at one end, and we can sometimes see an ionizing beam through the middle. Okay, and we go, oh, that's kind of bizarre. Okay? Ultimately, what really picked this up is they saw fluorescence. They saw photography paper change colors. Okay, well, why is the photography paper changing colors? It's changing colors because as something is jumping through this, it's emitting a form of energy which is causing the paper, the photography paper, to change colors. And by change colors, black to white, white to black. Okay? So not a big color difference. So they started playing around with this and dropped magnets near it. And what happened to that beam? It moved. Okay? That's giving us the evidence that whatever that particle is negative. That's giving us our charge. We also know that it's not an atom because we just removed all the atoms with a vacuum. Okay? So that means there must be something else that's contributing to that. That something else was our electrons. Okay? So after this, Thomson says, okay, well, that atomic theory of it being completely indivisible is false. We have to have electrons and protons in there to cancel each other out somehow. So what does he come up with? That's the plum pudding model. So he goes through and just says our atom is composed of a sea of positive charge, and we have these plum puddings of electrons in there. Before we get too excited about writing it down, because it is okay to write it down, right? The reason we're writing this down is because it's wrong. Okay? We're discussing this because this theory is inherently wrong. Okay? But with the data at hand, it's the best conclusion we can get. Okay? You did some reading. What do we know to be true about our atomic model? Is it just no, about the atomic model, period. What is the atomic model? We have protons, electrons, and neutrons. Do they all just exist in a sea of free-floating stuff? No. Okay. What's that?
They're clustered in the center.
What is clustered in the center?
Protons.
The protons and the neutrons. What's the charge on a proton?
Positive.
Positive. What happens when I bring the north end of a magnet near the north end of another magnet? They repel. What's going to happen when I take a positive proton and a positive proton and bring them near each other? They repel. At this stage, I only have evidence for protons and electrons. If I put all the protons in one place, it's going to fall apart. That's a bad theory. Okay? So based off of the context that we've got, it has to be somehow spread out. Okay? That's the theory he's working with. Okay? And that's what we're trying to use to explain everything. Okay? So what would I expect you to get from Thomson? So there's a lot of text, there are a lot of dates, all that fun stuff. So I would start with Thomson. It's a good place to start. What do you want to tie to Thomson's name? Okay. Protons and electrons. Okay. How did he discover the protons and electrons? And ultimately electrons and protons. Vacuum was the tool that he needed to make, I actually didn't say it, to make that thing. What was that thing?
Fluorescent tube.
It's not a fluorescent tube, it's a cathode ray tube.
I don't know how to write it.
Right? Also known as a CRT. Let that kind of sink in a little bit. Sounds like it's already sunk in the back appropriately. Right? Where do we see CRTs? Old school televisions. Okay, we've since advanced in technology, but televisions, you couldn't put magnets near them. Why not? It would mess with the CRTs, and that it would displace where the electrons were moving, and so you got different images coming out of it when you brought a magnet near it. Okay? So Thomson, electrons is the big thing. Protons are kind of a secondary aspect. Vacuums are useful to tie to him, and CRTs. Okay? He did have an atomic theory. Okay? I wouldn't memorize it as atomic theory. I'd memorize it as, we could say wrong theory, plum pudding model, and I might say false plum pudding model. Okay? I've now tied a whole bunch of those keyword concepts together. You'll notice it's not a complete sentence. It doesn't have to be a complete sentence, because when you read a multiple choice question, it's in a complete sentence, you have to be able to pull the keywords out. If you just pull out the keywords, you can now be able to answer that question better. Does that make sense? So 1, 2. So when it comes to the history stuff, for the most part, it's multiple choice. If you're curious about what kind of questions you would see, look at the practice exams. They're there. valence electrons is a concept that isn't even addressed at this point. And in fact, we probably won't address it today. Okay? This one's not in your textbook, but I like talking about it for a couple reasons. We get a little bit of history behind what science is and where it ends up going, okay? And just some of the painstaking effort that goes into it. So we'll start it off with Millikan and Fletcher. Millikan's the one that gets credit for this, okay? He's the primary investigator. If we look at kind of relationships, Millikan is me, you are Fletcher, okay? The way most kind of graduate science works is that you as a student would come to me and say, I like the work you're doing, I want to work with you, let me work in your lab. Okay? And I'd say, okay, here's the project you're working on, let me know if you've got questions, have fun. Okay? When you come up with results, you come back to me, we sit down, talk about the results, okay? Come up with conclusions, we write a paper together, we publish it. Okay? Who gets credit for it? Me. Okay? I get credit for I was largely the brain behind all of that. What you did was act as my hands. Okay? And yes, you contributed some of the thought behind that, but for the most part, a lot of that was me. Okay? What do you get out of that relationship? Well, if my name is good enough in the field, when you graduate from my group, you get a job. And you can now do the exact same thing to other students. Kind of make sense? So this relationship was an interesting one because Fletcher was like, I noticed you've been doing some cool stuff with electricity. Neat. I've got this idea that I want to study. Will you let me do it? And I said, sure. So Fletcher went out and designed his own experiments, okay, built the whole system to do it, analyzed the results, presented those results to Millikan, said these were the conclusions, and Millikan was like, those are fantastic results. They published those results. The Nobel Prize came around, and Millikan got it. Fletcher did not. Okay? Fletcher did almost all of the work and gets none of the credit. Okay? Which does kind of suck. That's a lot of how graduate science works. Okay? To his defense, Fletcher doesn't see anything wrong with it, and I sort of don't either. There's kind of a balance there. Okay? But Fletcher graduated and was able to get exceptionally good jobs because of his tie to Millikan. Getting the Nobel, he could have gotten a Nobel Prize, that's true. Okay? But he could just as easily go on to get a Nobel Prize in something else later on.
So he just not get it because he didn't like...
He wasn't the official person doing the organizing the group, yes.
Why don't they just do like a joint, I don't know.
And they can do joint prizes, and it just kind of depends. A lot of it just depends on the situation, and a lot of it is also the kind of context behind how those discoveries were made. Remember, the general trend is that you come to me saying you want to work for me, and I give you a project. Turns out that that wasn't the primary reason this relationship worked. Fletcher came to Millikan and said, this is what I'm going to do. Provide me the money to do it. Okay? Millikan still has to provide the money, still has to provide the grant research, okay, the facilities to do all of this. Okay? So Millikan is not a small contributor to this. Okay? It just turns out that Fletcher was a much larger contributor than in most circumstances. Okay? So he did graduate with a very good job afterwards. I don't think he ended up getting a Nobel Prize, but within the community acknowledges the effort that he's put in. Okay? You may not get as much of the fame because of the Nobel Prize, but the community still acknowledges that. Okay? So it's kind of neat for that. The other part that it's neat is the actual experiment itself. Okay? So they took a little perfume bottle, okay, and they sprayed out of the perfume bottle. Due to the friction of the perfume bottle, each of those particles carries a little bit of electric charge, okay, which is kind of neat. So when you spray that perfume bottle, you see the droplets kind of disperse, and they just then fall. Why do they fall? Gravity. They're going to fall with a certain force dependent on their mass. Right? Okay. So what they did is put a box around that, so now all the perfume stays in a box. Okay. And they put a small hole in the bottom of that box. Okay. What happens as the oil drops fall? The majority of them do what? Hit the box. Where does one of them fall? Through the tiny little hole. Underneath that tiny little hole, we've got a microscope aimed at it, okay, with an approximate focus set to that distance, so that when the drop falls through, someone looking in the microscope can be, there goes the drop. That's how big it was. So they can pull out a ruler and measure the drop. Try and measure a falling ball. Right, that's going to be a challenge, right? We would need it to be stationary to be able to get those measurements, right? Okay. How could we get it stationary? Well, remember the particle is charged. So also in this little system is a capacitor. That capacitor builds up charge on the bottom of that plate. That negative charge as it falls down, what does it see? A negative plate. And what does that mean? It repels, and so it jumps back the other direction. Okay? How much is it going to jump? Well, that depends how much current you're flowing into the capacitor. Since you don't know what the charge is, your dial on that current is going to be all sorts of crazy. Okay? So the first time it falls straight through. Well, it wasn't enough current, so you crank it up. Next time it falls through, whoa, and it launches back out of your view. Okay? So you got to keep dialing it in until you get to that proper spot. Remember, this is watching a drop fall and then ricocheting up or down. Okay? While you're looking through a microscope. Okay? Eventually, you'll get that current dialed in just right that what happens? It'll levitate. It'll sit right in that spot. During that spot, you can measure now the distance. Cool. So you could figure out the approximate mass of that particle. Okay? So you know now the downward force, because you know gravity and you know mass. What's the upward force? That's the electric repulsion. The electric repulsion from the plate that you know and the charge on the electron that you don't know. What does that mean? You can now solve for the charge on the electron.
Makes sense. Yeah.
That's kind of crazy. Okay? You're measuring a bunch of different things. What are the odds you're going to measure those things correctly?
Small.
Very slim. So what can we do to minimize that error in your measurement? Redo it. How many times should you redo it? Okay, lots and lots and lots of times. Simplest level, you have to repeat experiments 3 times so that you can get an average. Okay, they're probably repeating on the order of hundreds of thousands of times. Okay, they put all of that together, they average it out, and now they get a charge on an electron. How small is that number?
Very.
Yeah, that's really, really, really small. How close are they to the actual value? Like 96, 97% accurate. Right? Based off of newer technologies that we have. So that is insanely cool. So what do I want you to remember here?
Electron.
Millikan, Fletcher. What's that?
Fletcher didn't get the number first.
Okay, so there's a little bit of science bitterness in that. That's okay. I would argue I don't need you to memorize that for the test.
Okay.
The exact charge in the electron. What was the charge?
1.5924 to the negative 19.
Okay, so how many of you were able to do that without looking at your notes? Okay, there we go. That's a problem. Okay, that level of detail I don't want. So what do I want you to know? Millikan, Fletcher discovered the charge on the electron. What's the charge on the electron? I don't care. But they discovered the exact charge on the electron. How did they do it? The oil drop experiment. Okay? Now you've got them all tied. So now what you'd be doing is looking for those keywords. Kind of make sense? Okay. Millikan, Fletcher, oil drop, charge on the electron.
So we know, so we don't need to know the exact.
I don't care about the exact charge. Yep, complete waste of time.
Now, what is the C signifying as far as?
C is a coulomb. it's how we measure charge. Okay, so that's also why I'm saying don't worry about it.
C is in what?
It's Coulomb. I might be spelling it wrong. Coulomb. Coulomb.
Does that refer to like Coulomb's law or?
It's all based off of that, same principles. Okay, so let's go to Rutherford. Okay, when I talk about this, I like to think about this is that Rutherford hated Thomson, horribly untrue. Okay, and really the story that I now pitch is that Rutherford was just a dang good scientist. Okay, so Thomson and Rutherford were actually pretty decent friends. Okay, so let's say you wanted to prove Thomson right. So according to Thomson's model, okay, there really isn't anything to an atom. It's just a sea of random pieces. They had discovered these things called alpha particles. What they knew about alpha particles is that they were positively charged and they had a significant mass. That was about it. Okay? So if we look at Thomson's model, what happens if I fire a positively charged particle with significant mass at this? It should just pass straight through. Okay? If Thomson or if Rutherford only wanted to prove Thomson right, what should he do? Okay, so let's take these alpha particles, let's aim it at something, some atoms. We'll aim it at gold. Gold's nice and uniform, we can still see through it. So we'll aim our alpha particle radiation at this gold foil. Okay, and if I want to prove Thomson's right, what do I want to find? I just want to see it pass through. So if I'm going to study this, I have to have something to detect the alpha particles. Okay? So if I want to prove Thomson right, and prove is in massive air quotes, what am I going to do with my detector?
Leave one small spot.
I'm going to put one small spot on the back end of the gold foil. Now what happens?
It will always go through because of the air.
What I'm going to see is it all goes straight through. Ta-da, Thomson must be right. Rutherford liked Thomson, but he's a good scientist, and said, if we only do that, we actually don't know if it's doing something else weird. So while it may be more expensive, let's go ahead, and throw our detector all the way around the sample. We'll still see him just pass straight through, but why not? Let's just throw it up there just to now extra prove Thomson's right. And instead, what happened?
It was proved wrong.
Right? We proved him wrong. Why? We fired those alpha particles and we saw some scatter. Well, maybe they would scatter because it just sees a local positive charge somewhere. The more important one is that we saw particles reflect backwards. Okay? That makes no sense. Okay? The analogy the textbook or Rutherford used, the textbook told you guys about, is firing a bullet at a piece of toilet paper and it bouncing back at you.
Or what? No.
Okay? That's kind of crazy. Okay, so what does that mean? Thomson's model must be wrong. How must it be wrong? That particle had to have hit something. That something had to have mass. Okay? What if that something was just all of the plums, all of those negative charges put in one spot? Right? The alpha particle is positive. What happens is that positive sees the negative.
It attracts.
It attracts, in which case it would either stick or pass straight through. There's no reason for it to repel. So that massive thing can't be the electrons. Well, what's the only other thing we've got? Protons. So Rutherford says all of the protons come together, we put them in one spot. Okay? The majority of the time, our alpha particles aren't going to hit anything, and they're just going to pass straight through. But every so often, they will hit that one spot, and they'll bounce. That one spot is the center of all things. So we call it nuclear, right? Or a nucleus. That's why when we hear nuclear families, we're talking about supposed to be the standard form, okay? The center focus. Right? So we've got a nucleus now. Okay, that's kind of cool. before we dig into that nucleus a little bit, the question that I would ask is, what the hell is an alpha particle? And how do I get that?
It's a positively charged particle with a high mass, isn't it?
It's a positively charged particle with a high mass. Coming from where?
They're playing with radiation.
They were playing with radiation. So remember, at this stage in history, they're finding new elements. They're finding elements that when we put them out, they glow. Okay? When we set them on a piece of photographic paper, the photographic paper changes colors. Okay? Why is it doing that? We didn't expose it to different lights that we're used to seeing. It's in a dark room. Why is it changing? What is causing that? That cause is nuclear radiation. Okay? To do an experiment like this, we have to trust that what's coming out of here is 100% clean alpha particles. If there's any variation in those alpha particles, what we could be observing could be not an alpha particle bouncing, but something else. Right? So we have to know that what's coming out of that is pure alpha particles. That's problematic. Because for it to be pure, wherever the alpha particle is coming from also has to be pure. We're looking at radioactive things. Somebody has to isolate those radioactive substances. Okay? Not only do they have to isolate it, they have to share that information with everybody else so that we can play with this. Okay?
What if you were to use something else besides gold?
You'll see similar things. A lot of it has to do with the porosity, being able to pass through, and the lack of reactivity. Okay? Because if we fired something at it like a water cannon at gold, we might expect one result. But if I did it with lithium, what happens? Sodium, does anybody know? It goes boom, it disappears. Like, we get a big reaction. Gold is awesome because gold doesn't react. How do we know that? This is why we had like gold booms. What's happening? You go out and you dig in the dirt, and what do you find? Pure gold. Why pure? It doesn't react with anything. So we're going to expect a minimal interaction with using gold. If I pick any other element, there could be some other variable that I don't know about that could be messing with the results. Okay, so that's why gold is picked. Okay. So where do I get these alpha particles from? Somebody had to do this discovery. Who did that discovery?
Was that Curie's work?
That is Curie's work, which, not referenced in the textbook, by the way, okay? Madame Curie. Madame Curie went through and, or Mary Curie, I guess we should say. Madame is for a reason we'll address here in a second, okay? Comes from discovering and working with radiation, okay? The extra interesting things about, as the name might suggest, Madame Curie, is that she is female. You might be like, well, that's not a big deal. You know, we got women in this class. 1,900.
It was big.
Okay? That is a huge deal. Okay? And if anything, her desire to learn is what kept her going through. Because everywhere she went, they said, no, go away. We don't want you. Women don't do that. Women don't learn. Women don't contribute to science. And she kept just pushing and finding people that would allow her into labs where she was able to pick up that knowledge. So that's insanely cool. Okay? To give you an idea of how much her contributions were considered just the work of a woman and not valuable, she did get a Nobel Prize. Okay? The first Nobel Prize she got was actually because her husband refused the Nobel Prize. Okay? They were going to give the Nobel Prize to her husband, who she worked very closely with, okay, and a couple other people. And her husband said, no, I won't accept the Nobel Prize if you don't also give it to my wife, because my wife was the one that did the majority of the work. Okay? So she had a lot of support around her, contributing and helping her actually advance and get that kind of, not necessarily fame, but credit for the work she's done. Okay? Let's add to the coolness of Curie. There are two people in the history of the Nobel, or a couple people in the history of the Nobel Prize who have won multiple Nobel Prizes. Okay? I think it might actually be up to 3 or 4 now, but for sure there were only 2 for a while. Okay? Those 2 people happen to be chemists, chemistry school. Okay? One was Linus Pauling, who got a chemistry Nobel Prize, and he got a Nobel Peace Prize. Okay? I think it was actually peace. So not two science fields. Curie gets 2 Nobel Prizes one in chemistry and one in physics. She's the only person to have achieved 2 Nobel Prizes in science fields. And at the time, couldn't vote, wasn't allowed to work in research labs, okay, and had to scrounge and fight to get access to a lot of that knowledge.
Imagine if we had given her capabilities.
Okay, so that is insane. So her kind of history, I think, is a very good thing to address so that you recognize that everybody has the ability and value to contribute, and we should be looking at everybody's input into it, not just a select group of people. Okay? So I think it's a neat story. If you're interested in Curie, you should keep digging into her because she is kind of cool. Okay. So what should we remember for Curie?
Discovered alpha.
Okay, alpha particles coming from
Radium?
a radioactive element. The big radioactive elements that she discovered were radium and polonium. Okay. Those radioactive sources were of critical importance to what? To Rutherford's experiment. If Curie doesn't release this information, Rutherford can't run his experiment. Okay, which is the other reason why I like Curie, so we'll bring that up. Okay, you discover the cure to cancer. What do? You just had it. There it is. You've got it in your hands. What do?
You keep it to yourself.
Okay, share it. You keep it to yourself. That it's a new one.
How do you spell her name?
Curie. Okay, write it down in pen. Patent it. Why would you patent it? So you could monetize it. Right? And that's not a horribly wrong thing to do, so don't freak out at that. Okay? But that's one of the big issues that we encounter in science now. We've been looking at pharmacology and different pharmaceutical companies saying we have to charge $500 per ounce of this drug because that's how we're funding our research. Okay? We do need money to come into research. That's why we monetize it. The question becomes is how much are you monetizing it? Are you monetizing it so that you become more profitable, or are you monetizing it so that you can continue to do more research? Okay? So the two kind of extremes is patent to make crap tons of money, or open source it and make sure everybody has access to it. Curie open sourced. Okay? Doesn't get any credit, right? Horrible politics going against her, and she effectively helps people to study this more for free. That's kind of cool.
It was radium and what else?
Polonium. Okay. So Curie releases that information so that Rutherford can do his experiment. So Curie, radium, polonium, alpha particles, leading to Rutherford. What do we know for Rutherford? Nucleus. How do you discover the nucleus? Using alpha particles. Alpha particles becomes a questionable one to tie to Rutherford because you've already tied alpha particles to Curie. So don't tie alpha particles to Rutherford. Gold foil. Okay? Make sense?
We just called it gold foil experiment.
Yep. Okay? So, Rutherford goes through and changes the theory for Thomson, and we end up with the creation of a nucleus. You'll notice there's red and blue particles in there. Why are there red and blue? Because they'd be different things, right?
Yes.
Okay, and so we're going, oh, there's protons and neutrons. What particles have we discovered at this point? Electrons and protons. Rutherford is not saying to put electrons in the nucleus. He's saying only to put protons in there. Why did Thomson not do that?
Because they should repel away.
They should repel away. So Rutherford says, we have to put all these things here, and it has to be positive. There's going to be so much repulsive force that not only do we have to have these alpha particles there, we are also going to have to add some glue to hold it all together.
So
That glue is not charged, so we're going to call it a neutron because it's neutral.
never mind. You answered my question.
Right?
So he discovered the neutron too?
He did not discover the neutron. All he's done is said it has to be there.
Okay.
Okay? I know it has to be there because the protons should repel away. There has to be something else in there. I don't know what it is, but there has to be something there. Okay? Before we move on just a little bit further, just to give you an idea of scale, because I think this is kind of neat. Okay? An atom has a diameter of about 10 to the minus 8 centimeters. So a centimeter, think about your fingernail, about a centimeter, ballpark. Okay, 10 to the minus 8. Okay, just divide your fingernail into tenths, now hundredths, now thousandths. Now what is it, 10 thousandths, 100 thousandths? We're not even close yet. This is insanely small. Okay, so that's just the atom. If we look at the size of the nucleus, it's 10 to the minus 13. Okay, for people that look at those numbers, it's like, yeah, that's really small. Okay, your brain sucks at dealing with numbers. Okay, it does a horrible job of it. Okay, what is the largest number that the human brain can deal with well? 100, a billion, a million. Okay, and I'm going to say 100, million, and billion are all wrong. Why are those all wrong? We literally invented a word to describe the number.
1 to 10?
10, because we have 10 fingers. Okay, it's the easiest way for us to count out. And people go, that's not true. I can definitely deal with 10 or numbers larger than 10. I'm going to go to the store and I'm going to buy some eggs. How many eggs do I buy?
12.
I'm going to buy a dozen eggs. I literally invent a word to describe two numbers larger than 10.
What about
The
20?
human brain does not do well with numbers larger than 10.
What about 20? Because you have 20 with the toes.
Okay, so you could do
Increment.
20 fingers and toes. First, you would have to
Take off your shoes.
take off your shoe. Okay, so I would argue 12 is our max capacity because we get 10 fingers, 1 foot, second foot. I can deal with 12. Anything higher than that, I'm now going to recycle. So, dozen. There it is. Okay. There are other ways that we can manipulate and add layers to that. Greg talked about that, looking at the digits. Okay. But again, that requires a slightly larger cognitive effect. So those numbers are too difficult to deal with. So what do? Let's pick an analogy. Let's take a football stadium. Right? We don't have to use the Superdome because I don't know what that looks like, but I know roughly what ASU's football stadium looks like. We take ASU's football stadium, okay? We take a marble and you put that in the football stadium. The football stadium is the size of the atom. The marble's the size of the nucleus. That's a really big difference. Okay? So we are literally taking all of those protons and jamming them into the smallest, tiniest possible spot. Okay? That's kind of crazy. Okay, so Rutherford predicted that we have neutrons. He predicted that because of that repulsive force. It wasn't until Chadwick comes along in 1940, 1950, and actually has an experiment that discovers a neutron and says, here's the evidence that we actually have a neutron. Here's the particle. Okay? Fun little bit of information about this. Okay, so Chadwick, all I want is neutron. That's it. That's all you got. Okay? Thomson started this whole chain, right? Followed by Rutherford for our atomic structure, right? Rutherford had to learn from somewhere, right? Who did he learn from? Thomson. He got data he got radioactive pieces to study for his model, but he studied under Thomson. Rutherford was Thomson's student. Chadwick was Rutherford's student. Okay? It's not quite nepotism, right? Okay? But we're seeing that technology advance from one research group to the student to the student. We're seeing it actually build through kind of history and those people studying. That's kind of cool. So, big thing that you need, giant red box. Everything in this box you should know. Okay? We're looking at symbols, we're looking at notations for how we approximate and envision these. We're talking about where these things are located. So that is of critical importance. Unfortunately, don't take a picture yet, because one of those things is not in the realm of 1 through 10. Right? 1 over 1,836. Okay? Do you really want to memorize that number? If you do, find a different class. Okay? How big is that mass? It's really, really tiny. Does hair have mass? Yes. So if I want to lose weight, I need to shave my head.
Maybe.
You're like, yeah, you lose weight.
Not a lot.
Not a lot. If I shave my head and step on the scale before and after, am I really going to see a mass difference? No. So for the mass of an electron, it is so insanely small, that we will actually say the relative mass of an electron is 0. Now if you want to take a picture, you can. Hi?
That's me. I don't have computer presentation to take a picture.
Hi? So you need to know all of those pieces. Those are all going to be of critical importance. And the part that's going to become really critical is that we then need to be able to apply that knowledge. It's not just that fact, it's how do we apply it further on. Okay. Oops. Yes.
Sorry, so how was the order again?
It was.
Oh, from scientists?
Yeah.
Thomson, Rutherford, Chadwick.
Do you know the order?
No.
No, it's just a better.
It's just neat. I think it's neat.
Can you go back for just a second?
Right. This table is in your textbook. It's table 4.1. Right. We will see it show up again in a slightly different version later in the slides.
Does it say 1 over?
It says 1 over the 1,836. A lot of textbooks will push for super accuracy, even when that accuracy is not useful. Right. Which gets us actually into atomic notation. Okay, which is a fun one for me to talk about because I think it is not called atomic notation. Okay? Or not appropriately called atomic notation. Okay? So when we think about atomic notation, we're probably talking about describing what? An atom. What's in an atom? The nucleus. What's in the nucleus? Neutrons and protons, followed by electrons, right? There's 3 things that go into an atom. Let's take a look at our notation here. Okay, we could look at the text, but we've got the symbols all written out here. What particles are accounted for in this notation? Protons and neutrons. Have we talked about the electron? No. The electrons aren't showing up in this notation. They're technically implied, and we'll fix it to make it more atomic notation here in a second. Okay? But this is not describing an atom. What is it describing?
The nucleus.
The nucleus. Okay? This is nuclear notation.
Is that in your opinion or is that
My opinion.
Which one?
Okay? So it will get called atomic notation always. Okay? Who would care about nuclear notation?
Scientists.
Nuclear physicists. I'm a scientist, I don't care about this notation. Okay? Nuclear physicists would care about it. Someone studying nuclear bombs, okay? Nuclear energy is going to care about nuclear notation because they care what's in the nucleus. Why? When we build out that nucleus, we're putting more protons in each and every single time, right? The more protons we put in, the more neutrons we have to put in. The neutrons effectively are a glue holding it together. Okay? So if we envision a proton as a positive charge, okay? If I'm going to build the nucleus, I'll take one marble, a second marble, and I bring them together. But they're going to repel, so what do I got to do? Glue. Glue's a little wet, but, it's just 2 of them. They'll probably stick eventually. What happens when I want to build a larger nucleus? More glue, more marbles. So we restart. We don't get to dry it each time. We restart. Okay? What happens if I get up to, say, 57 marbles? That's a lot of glue. Okay? Is the glue going to dry very well by the time I get the last one on? No. So what's likely going to happen? It's going to fall apart. Guess what that falling apart is? Nuclear radiation. As a nuclear chemist or a nuclear physicist, I care about the size of the nucleus. What things go into the nucleus? Protons and neutrons. So if I'm inventing now a notation that allows me to study and represent these things, the very first thing I'm going to want to see in my notation will be the protons and the neutrons, because those are all the things going into the nucleus. If we take a look at the notation, what's the very first thing you encounter?
AZ.
We encounter the A, because we read left to right, top to bottom. That A is the protons and neutrons. Why do I place the mass number there? Because I'm a nuclear physicist and I want to see if it's radioactive. So if I see a massive number there, that's probably radioactive. If I see a 12 there, it's probably not radioactive. I don't care about it. Okay? So I'm inventing my notation so that I can find that information faster and quicker. That sounds kind of like the technological aspect of writing. Okay? Because we are organizing the information in a way that cognitively allows us to understand it and interpret it.
So on the table, the number in the corner, is that the mass?
So the next thing you might ask is be looking at the periodic table versus looking at this. So the mass number, protons and neutrons, upper left-hand corner. We take a look at a symbol. Let's take a look at the bromine, the big one, in the middle. What's written in the upper left-hand corner?
Nothing.
Nothing. Is it atomic notation or nuclear notation on the periodic table? No. What notation is it? Whatever the hell notation they felt like. It's not the same notation. Okay? Why might it not be the same notation? Who needs nuclear notation? Nuclear physicists. Who needs the periodic table? Everybody freaking else. Okay? I don't care that it's radioactive because I'm never going to see it. So I don't care about the mass number. I don't want to see that cluttering the very first thing I pick out. Does that make sense? So we're going to change and emphasize or de-emphasize certain aspects of that information so that I can pull to it quicker. Right? So back to our nuclear notation. After I figured out the mass number, what might be the next most useful thing? Atomic number. Because when you lead from top to bottom, right? So you just take the left-hand side and you just read straight down. So if we go through and read the paragraph up above, it is each the we element nucleus total atom use neutrons. Those are being like, no, that's stupid. Careful how we read. How do we read? Left to right. What's the very next thing we encounter? The symbol. We now know the symbol of the element. That helps us identify where it is. Okay? And then we could cycle back down to our atomic number. Is that useful information? Atomic number is the protons, right? If I tell you C, what do you tell me for protons? 6. How'd you come up with that so fast? You looked at the periodic table where it said C, and the atomic number is written in the upper right-hand corner, and you know it's up in the upper right-hand corner because the key tells you that. You are now chemists. When do you have a periodic table? Always. If I tell you O, what's the atomic number? 8. If I tell you 16, what's the symbol? That was interesting. That was a little bit longer to get to. Okay? Once we know the symbol, the atomic number is redundant information. Okay? Which could be a good reason why it is written on the bottom. Okay? It's not as important. If I want to follow the absolute strict sense of atomic notation, that is the order I have to follow. Are you asked test questions on that? Yes. Is it incredibly stupid? Yes. You're still responsible for it. Okay? I said we could bring in electrons, right? Okay, where else do we have space on that object to write things? On the right-hand side. Just the right-hand side? Top and the bottom. You actually know information already about what belongs in those spaces. You know this one. What goes in that space? You're like, damn, I do? What's the formula for water?
H2O.
What goes in that space?
The number of molecules.
It's the quantity in your formula. What goes in the upper right-hand corner? Okay.
Number of electrons.
What's the last missing piece? We need information about our electrons. Okay? But just like how we brought in our neutrons, we brought in the neutrons in the context of our protons. We're going to bring our electrons in the context of protons as well. Why protons and not neutrons? What do protons and neutrons have in common?
The nucleus.
Positive
They're both in the nucleus.
charge.
They are both in the nucleus. They're both the same mass. What do protons and electrons have in common?
They're charged.
They're both charged. So that upper right-hand corner is the protons and the electrons coming together to give us the charge. This can become tricky because if we take a look at a single element, let's pick one really quickly. If I picked carbon, okay, actually let's do carbon, and I just write it like that. What is written in the upper right-hand corner? On the periodic table, it is 6. The periodic table is not atomic notation. What is written in the upper right-hand corner? I know I put a box on it.
Charge.
The charge. What's the number written in the upper right-hand corner?
12.01.
So I know you're looking up there. That's cool. There's a reason I'm literally pointing at the upper right-hand corner. What is the number written in the upper right-hand corner?
No.
There is no number. How many electrons are there for this carbon?
Zero.
Negative.
Okay, I heard 0. Well, there's 0 there, right? Okay, it's protons plus electrons.
So -6.
So -6. I have less than the existence of an electron. How many protons are there?
6.
6 for carbon. And now we're asking how many electrons. The charge is what?
Negative.
The charge is what?
Sorry,
0. So there was a suggestion that it needs to be -6 electrons. I can't have less than an existence. That doesn't work. But when we're adding here, what are we taking into consideration also? The charge. The proton is positive. The electron is negative. So if I take 6 electrons and add them with 6 protons, what becomes the overall charge?
Zero.
0, because the electrons will counterbalance the protons. Okay? So with that, I got to stop because we're way past done.